All right, this may be another long video, so hold on to your hats. Rationalizing with the radical with exponents. So now we're not just rationalizing numbers like we did for the last one. We're working at it with these variables as well, x to the sixth and y to the eighth. Very similar to that first one I did, the 16 x to the eighth, y to the fourth, I think. So when we're rationalizing this, we want to first start by looking at the number. So we've got 27, x to the sixth, y to the eighth. Now, I already told you in an earlier one that 27 is the same as 3 times 3 times 3. And so we already know that the cubed root of 27 is 3 because that was in the other video. And so we can bring that 1/3 through. We can rewrite it as an exponent, 1/3. 27 to the 1/3 power, you could do your factor tree and say that's 3 times 3 times 3. That's the cubed root of 27 then. If it's x to the 6/3 and y to the 8/3, we can reduce that. Now, it seems like I've already done this, but it's a little bit different now because 6/3, we can reduce that very easily. 6 divided by 3 is 2, so it'd be x squared. But 8/3 is a little bit different. So now we have to figure out what to do if it doesn't reduce down all the way. 27 to the 1/3 again, 3. 6/3 for x was 2. Y to the 8/3, I'm going to write that as a mixed number. Now, this is kind of the longhand way of doing it. I'm showing it in a lot of extra steps. But 8/3 is like 2 and 2/3. So we got that mixed number here. So it comes out 2 times evenly. There's a full 2 groups of 3 y's with 2/3 left over. The way we would finish this is like this. And I'm going to give you a visual of how that happened here in a second. But this 8/3, there's basically 2 full groups of 3 y's. Here's that y squared, 2 full groups of 3 y's, and 2 left over. So that's where this y to the second power is in here. There's 2 leftover y's of these cubed roots. That's confusing enough just me saying it. Even me talking about it feels confusing. So I'm going to expand this out. So 27, x to the sixth, y to the eighth. That's what we have here. That's what I've written right here. 3 times 3 times 3 is 27. X times x times x times x. Got 6 x's and 8 y's. Because I'm taking a cubed root, I'm looking for groups of 3. There's 3 3's. So here's that 3 right there. I pulled out 1 full group of 3 3's. There's 2 sets of 3 x's. 3 x's and another 3 x's. So I'm able to pull out 2 sets of x's, x squared. There's 2 full sets of 3 y's, 3 y's, 3 y's. So there's that y squared there, 2 sets of 3 y's. And there's 2 y's left over. So this is basically like that factor tree. We factored the 27 into 3's, and we've expanded those x's and expanded those y's. So those 2 leftover y's are what we see right here. So the cubed root then of y squared. All right, adding and subtracting radicals. If we want to add things, we need to have a common label. Just like fractions, you need to have a common label. So if we're adding things together, we have a common label. If we're having 4x plus 3x, that works. 4x plus 3y, we can't combine that together. This is what we're finding here. We've got 4 of these, the square root of 54, plus 3 of these, square root of 24. Square root of 54, square root of 24 are different, so we can't combine these together. However, there's a solution for that. There's a way around that. So let's move over to our document camera. We're going to do 54 and 24 and see what we can make of those two radicals. Okay. All right, 54. Let's do a factor tree. So 54 is going to be what? 7 times 8. Times 8 is 54. 8 is going to be 4 and 2. 2 and 2. 7 is prime. 24. All right, 24 is going to be, let's go with 3 and 8, 4 and 2, 2 and 2. Wow, it must have been a long day today. 54 is not 7 times 8. 7 times 8 is 56. I apologize if anybody was confused. My apologies. Believe it or not, it's a Friday. 54 then is going to be 6 times 9. Let's try that. That seems a little bit better. 6 is going to be 3 times 2. 9 is going to be 3 times 3. That seems a little bit more reasonable. All right, we're doing square roots, which means we're looking for groups of 2. I've got 2 2s here, and I've got a 2 and a 3 left over on that one. I've got 2 3s here, a 2 and a 3 left over. So this square root of 24, I'm going to write this above it here. We've got 3. That 3 is still there. We've got one group of 2, so 2 can come out. Got a 3 and a 2 left over. Here we have 4. That 4 doesn't go anywhere. I've got a group of 3. Pull out, and a 3 and a 2 left over. What I end up getting then is if I multiply 3 times 2 together, that's going to give me, over here, 6. So that's going to give me 6. That's going to give me 6. 6 root 6. So 3 times the square root of 24, I've simplified that to 6 root 6. 4 times 3 is 12. 3 times 2, square root of 6. Now I have a common label. Square root of 6, square root of 6. I can combine those together. It's like having a common denominator. So I've got 6 square root of 6 plus 12 square root of 6 is going to give me 18 square root of 6s. And that would be the solution. So 3 square root of 24 plus 4 square root of 54 is going to give me 18 square root of 6. By rationalizing those radicals, I was able to get a common thing that they have, a common label basically, square root of 6 and square root of 6, which allowed me to combine them together. That's what we see here. Okay, multiplying radicals. Multiplying radicals is a little bit easier in that we really just have to multiply the 2 times the 6. 2 times 6 is 12. And the square root of 3 times the square root of 7. If you remember back to this slide here, the square root of a times the square root of b, we can just combine them together and multiply inside of one radical. So if we go back to this one, this one, the square root of 3 times the square root of 7 is just going to be the square root of 21. So multiplying radicals is a little bit faster in that you don't need a common denominator like you do for adding. We just multiply the radicals together, multiply the whole numbers together, the coefficients, I guess, together, and get our result. Multiplying radical polynomials. Now we've got some adding and subtracting, something to be careful of with this one. Okay, I'm going to move over to the document camera to work this out. Or I should probably have the problem written down. Square root of x plus 6. Go. Okay, we're going to distribute our FOIL, however you want to do it, just like we have for other polynomials. So I'm going to distribute through the parentheses. Just square root of x times 3 square root of x. Well, the square root of x times the square root of x, it's just x. That worked out well. And the 3 is, there we go. So I put the extra times there. You don't necessarily need it. But 3 root x times the square root of x is 3x. The next one, the square root of x times 2 plus 2 root x. 6 times 3 root x, 18 root x. And 6 times 2 is 12. If I'm going to combine things together, they need to have a common label. The square root of x and the square root of x are the same, so we don't need to worry about rationalizing anything. We can combine the square root of 2x plus the square root of 2 root x plus 18 root x to get 3x plus 20 root x is 12. These are different. That's it. That's our solution. So the only difference here between what we did in earlier in the chapter with polynomials and what we have here is that the square root of x times the square root of x is just x, not x squared. I'm going to stop it. I only have 2 slides left. However, I think we're going to need a whole new video for those 2 slides. So here we go.